Hello and welcome to this film all about the electromagnetic spectrum. You might wonder, I suppose, what this is doing in the middle of a series of films about atomic structure, but we're about to start looking at things called line spectra, and these are much easier to understand if you know a bit about the electromagnetic spectrum before you start, and also it helps us understand some of the things that are going on in periodicity topic when we start looking at the colours of complex ions and so on. But anyway, for now, let's see what we're going to try and achieve by the end of this film. Hopefully we'll understand what is meant by the electromagnetic spectrum if we don't already know, and we'll know how we can relate the speed, the frequency and the wavelength and the energy of electromagnetic radiation, or what most people would call light. Now, light, although it's something that most people normally consider as being something that you can see, light is just a range of different wavelengths of electromagnetic radiation. Okay, and we could picture these different wavelengths in a chart like this one. So I suppose if we're thinking of a wave, okay, and we're saying that light travels as a wave, just like any other wave, we can measure the wavelength of that wave as being the distance between two peaks or two troughs or two halfway ups, whatever. Okay, so what we can see is that there's a very, very broad range of different wavelengths. These here are given in meters, and there are things called gamma rays, which have very, very short wavelengths. There are things called radio waves, which have wavelengths of 100 meters or more. And there's a very little range here in the middle of wavelengths which we can actually see. This is called the visible range of the spectrum, this kind of bit with the rainbow in, okay? And you might know that the range of colours that we can see goes from red through orange to yellow to green to blue to indigo to violet. Or Richard of York gave battle in vain is how English kids learn that, because Richard of York was an English king. But anyway, beyond the red end of that visible spectrum is the infrared range. These are waves that are slightly too long for us to see, and beyond the violet range is the ultraviolet range, which has wavelengths that are too short for us to see. Just like there are sounds which are beyond the range of our hearing, there are electromagnetic waves which are beyond the range of our vision. Okay, so just while we're here and we've got Roy Gabiv up on here, just a little curiosity that you might be interested to know, that there's 7 colours here, and the reason for that is because when people were first looking at this spectrum, 7 was a very special number. They saw red, orange, yellow, green, blue and violet, but that's only 6 colours, so they decided that they should name a new colour. Well, the colour wasn't new, but they gave a new name to indigo so that they could have 7 colours on here. Anyway, so that's what the electromagnetic spectrum is. It's a range of different wavelengths of light. And what you probably need to know in physics, or you don't need to know in great detail in chemistry, is that the energy of light, so that's E, is related to something called Planck's constant multiplied by the frequency of the light. Now, I learned that as being represented by Greek lowercase n, or nu, so E equals h nu, but quite often you see it as E equals hf. So E, the energy of the light, or the energy of a photon, is equal to Planck's constant multiplied by the frequency of the light. Not only is the energy related to frequency, but the speed of light is related to the frequency. And this is a statement that could be made about any wave, not just a light wave, but the speed that a wave travels at, so c is the speed of light, the speed that it travels at is how many wavelengths it carries out per second. Okay, so in other words, the wavelength multiplied by the frequency. Okay, and you can see that if E equals h nu, or hf, then E is also equal to, well, what's the frequency? C over lambda multiplied by Planck's constant. Okay, so the energy of the light is related not only to the frequency of the waves, but to the wavelength. And the longer the wavelength, the lower the frequency, And yes, that's right. The longer the wavelength, the lower the frequency, and the shorter the wavelength, the higher the frequency and the higher the energy. And that's kind of shown here, that gamma rays with their very, very short wavelengths and very, very high frequencies have a lot of energy. Now, again, you might wonder, what the hell has this got to do with atomic structure? Well, that will become clear in the next film, which is about line spectra. But hopefully now you, if you didn't already know a bit about it, you know what's meant by the electromagnetic spectrum, and you know how we can relate the speed, the frequency, and the wavelength and energy of light using a couple of formulas. As I say, you don't really need to know these formulas or formulae in detail in chemistry. You probably will if you do physics. But for now, it's good enough to know that high frequency light has short wavelengths and has a high energy. As usual, if there's anything in this film that you came across that you feel you'd like to ask a question about or comment on, or if I've made some howlers that you'd like to tell me about, then please feel free to comment on YouTube or come and see me. We can talk about the questions that you might have.